Okay, so here's where we were last time. We were talking about the equations of lines. We were basically reminding ourselves of a bunch of old Algebra 1 stuff from middle school, probably, right? And the idea was this, that if you have a point on a line, and if you have a normal vector perpendicular to the line, that characterizes the line, right? There's only one line that could possibly go through that point and be perpendicular to that vector. And we made an argument based on the idea that, well, look, this point is on the line if and only if this difference vector is parallel to the line. And from that, we noted that, well, parallel to the line means perpendicular to the normal vector, and perpendicular means a dot product is equal to 0, et cetera, and we got ourselves an equation for the line. Right? So really the main reason I do that is a segue into how we can apply those same ideas in a three-dimensional context. Right? So suppose I want to understand the equation of a plane. Right, how am I going to find an equation for a plane? Well, first I need some objects to describe it. You got to give me some information to define what plane you're even talking about. So give me a point in the plane, and then give me a vector perpendicular to the plane. Just like we did for lines, just sort of, appropriate to the context. Again, that characterizes the plane. Again, we can make the observation that a point is in the plane, on the plane, if and only if the difference vector, x minus x naught, is parallel to the plane. The point's on the plane, that difference got to be parallel. If the point's not on the plane, then x minus x naught will not be parallel. And everything kind of follows through just like previously. Parallel to the plane means perpendicular to the normal vector. Perpendicular means dot product is 0, dot product is algebra, fiddle around with some algebra, and out comes the equation of the plane. And notice it looks exactly like the equation of a line in R2. Right? So the only differences, of course, are these are now three-dimensional vectors, hidden by the fact that we're using vector notation, of course. But this normal vector in, right, there it is, and you see it has 3 coordinates, not 2. Likewise, the point that we're testing, this x point, we'd like to know if that is or is not in the plane. That has 3 coordinates, x, y, and z. Right? So this dot product here is now not just ax plus by. This dot product is now ax plus by plus cz. So if you want to expand it all out, this is our new equation of a plane. But honestly, very often, expanding things out is not only unnecessary, but arguably counterproductive, right? Kind of in some sense, these equations are really the exact same equation, right? But in this form, you can see what's playing what role. You can see that there's a normal vector in there, right? You can see that we're making an argument about dot products. This is arguably a more transparent version of the equation of the plane. So I like this one better. And that's what I encourage you to think in terms of. Okay. So, for example, suppose I want to find the equation of a certain plane here. I got a plane, and the information that I'm given is not exactly what I need. I'm given, let's say, 3 points that are on that plane. How am I going to go about finding the equation of the plane? Well, notice I don't have a normal vector. So I can't just say, here it is, right? I don't know the normal vector yet. I do know an x naught. In fact, I have a bunch of choices for what to be my x naught. You could pick any of these. If you want, p to be your x naught, okay, cool, whatever. It doesn't matter. Take a pick. So how do we get a normal vector, though? This is a little geometry puzzle. There are a lot of little geometry puzzles that come up in this whole section with lines and planes and stuff. And in this case, think about what we have, think about what we need, and then try to figure out how you can get there from here. Right? So, I have a couple of points in the plane. Their differences then are parallel to the plane, and I refer you back to the previous section. If you have a couple of vectors, the cross product of those two vectors is perpendicular to both of them, and therefore perpendicular to the plane that they're parallel to. Now, there's a geometric appeal. You got to think that through. Persuade yourself that if our cross product is perpendicular to those two blue vectors, it also has to be perpendicular to the whole plane. You got to see that geometrically. Okay. And since I now have a vector that's perpendicular to the plane, I can choose that to be my normal vector. Is everybody on board? Everybody see what happened there? Everybody see the puzzle aspect of this, right? So this is not an algorithmic, here, plug into the following algorithm and it always works, right? I mean, this is awfully narrow, I suppose, if it's an algorithm, right? But the idea is we have various tools that we understand have various features, and we've thought through a clever way to use our tools to take what we have and turn it into what we want or need. Okay. All right. Okay, so let's talk about lines in space. We're going to define something called a parameterization of a line. The book calls these parametric equations, and I suppose that's fine. It kind of rubs my fur backwards a little bit because this word equation, I shouldn't put an X through it, but I'm going to put a frowny face through it because the word equation, we just got through making a big deal out of the fact that an equation is a test. Right? That's the equation of a shape says, this will be my test. You come to me with a point. If it passes my test, it's on my shape. If it doesn't pass my algebraic test, it's not on my shape. That's what an equation is. Fundamentally, a parameterization is a different thing. A parameterization does not test points. It generates points. It's a fundamentally different kind of algebraic object in relation to whatever your shape is, in this case a line. Right? So that's why, but it's not playing the role that equations do, so I think it's suboptimal to think of them as equations. And I know technically they're going to be equations, that'll be clear. But anyway, I encourage you to say parameterization. Okay, so here's the idea. Suppose I know a point on the line, and notice it would be weird for me to try to describe this line it's perpendicular to that vector. Our old game from R2, right? Now, notice we're in space now, for example. We might be in space. If I try to describe that line by what's perpendicular to it, well, there's lots of lines that are perpendicular. Right? If we're in space, we've got sort of different directions in which we could go perpendicular to that blue vector. So perpendicular is not a good way to do this. What we're going to do instead is suppose that we have a point on the line and a vector now parallel to the line. These will be our two objects to describe this line. And simple appeal. If I start with a point on the line, and then if I take that vector, v, and if I multiply it by some scalar to give me tv, right, that vector tv still parallel to the line. If I were to then add a point on the line and a vector parallel to the line, that's going to give me another point on the line. So it generates points that are on that line. How are we doing? Everybody see the idea there? And that's a very different sort of geometric argument compared to when we were making equations of lines and equations of planes. We did not create a test. We created a little point factory. Right? Yes?
Is x not the point or a vector?
X, well, it's we're thinking of it as a point. I mean, keep in mind, there's a perfect pairing between points and vectors. We're thinking of it as a point because we want to talk about its location. So it's playing the role of a point. So yeah, let's say it's a point. Yep. And but then maybe this is what your question is. We're taking that point x naught and we're adding this vector tv, right? And point plus vector, and this is this is why it's in some cases, very convenient to kind of blur the distinction between points and vectors. What I mean by point plus vector is interpret the point as a vector, right? Do vector-vector addition, and then reinterpret the result as a point. So head to tail, it's just like we've got drawn here, right? But yeah, it's a little bit different. Yeah. It's a great question. Thank you. Okay. All right. So there's our little point factory called a parameterization. How do you think about this? There's different ways you can think about it. Notice that in this description here, I did not make specific use, any specific interpretation of what T is, but it's very common and very often convenient to think of T as being time. And if you do, then it's like, okay, well, when T is equal to 0, you're at that starting point, and then as time passes, by the time T is equal to 1, you're at x naught plus V. You've moved over a little bit when T gets to 1. And then as more, if you will, time passes, you get to this next nearby point, you might say, etc. And here's a little movie of this parameterization as time passes. As T increases, if I think of T as time, we are literally tracing out the line to generate the line. So it's a convenient way. This whole thinking of T as time. It's convenient because that's how we actually draw lines, right? We go like that. We don't have like a line stamp that where we just make it create all at once. So it's a familiar. It connects us to a familiar sort of process of how we write lines. The other thing is sometimes, very often actually, there really is a particle moving along the line, right? And so what we have here is a tool for describing position as a function of time, an actual physical thing. This is how we're going to describe physical motion, is giving position as a function of time. So it's a multi-convenient interpretation. Okay. Now, I want to recognize there's different ways that I can draw out this line. So this parameterization here, you might say, is this drawing of that line. But look, I could draw that line faster. Same line, just drawing it faster. This draws it faster. Right? It's still talking about the same line. It's still generating all the same points. I'm just doing so with a greater velocity vector here compared to a shorter velocity vector there. Right? I start at a different point here. I'm starting at 3, 4, which is starting there, as opposed to over here. I'm maybe starting there. So, yeah, there are different ways of tracing the same line, and in the same way that it is perfectly obvious that, of course, there's lots and lots of ways to trace out a line, that means it's easy to see. There's lots and lots of different ways to parameterize a line. A parameterization is not unique. There's zillions of them. All right. Okay, so let's consider this scenario. Suppose we're looking at a line in R2. On the one hand, we could have a parameterization of that line. On another hand, we might very reasonably have or want to have an equation of that line. How do you turn an equation into a parameterization? How do you turn a parameterization into an equation? Let me say that a little bit differently. Suppose you have a point tester, but what you really need is a point generator, or vice versa. How do you turn one of these kinds of things into one of these other kinds of things? And there's a lovely little argument here. It goes like this. Let me just talk about the algebra here. This parameterization, I'm just going to write it one coordinate at a time. There it is. I'm just expanding coordinates. That's all. Okay. Keep in mind what this thing here means. This says if you give me a value of t, a single value of t, then out will come a point that satisfies these two equations. Now, let me say that thing differently. If you give me a single value of t, right, that will generate the point, meaning that one single value of t will simultaneously generate the correct x and the correct y coordinate for your point. Well, if a single value of t is going to do that, what that means is that t and this t have to be the same. Right, the value of, if there's a single value of t that generates the correct x and the correct y, all for a single value of t, well, then that x and that y have to require the same value of t. It's almost a sort of a freebie. These are the same, therefore these are the same because they're both t. Okay, so that being said, notice we have here then an equation for a plane. Right? So in other words, there can exist a single value of t that is both of these things only if both of these things are equal to each other. Right? Okay. So notice we've turned then a point generator into a point tester. And this is a familiar form of an equation for a line in 2 dimensions. Okay. If you want to turn it around the other way, how do you turn a point tester into a point generator? Well, this equation, these two things being equal, since they're equal, I can call them both t. They're the same thing. Right? And I can then see, all right, well, given a value of t, if this is given, what value of x, what value of y do I correspondingly get? And well, you just go through this algebra, and there's your parameterization. So, kind of a nice little process there. It's just a matter of recognizing that an equation means two things are the same, and if they're the same, then you can give it a name. Okay. All right. Likewise in 3 dimensions. Totally analogous. If you have a parameterization of a line in R3, that parameterization, you can write out individually the separate coordinates. These x's, y's, and z's are all generated by that same t. That same t, then, being as it is a single thing, all of the things that it's equal to are equal to each other. Again, it's sort of tautological, right? And there you have a point tester. Now, here's the weird thing. This isn't familiar, right? We've never previously written down an equation for a line in 3 dimensions, right? We didn't have that before. So this is not our old friend, right? This is a new thing. It's not an equation. I'd like to call this the equation of a line, but really importantly, it isn't. It's at least 2 equations, and it's arguably 3 equations if you point out that, well, we need those things to be equal, right? So again, it's sort of, of course, this third one is an immediate consequence of the first 2. But you might think of it as 3 equations, and we're momentarily going to do that. But anyway, because this is multiple equations, I'd have to call it the equations, plural, of the line. And in fact, we call this the symmetric equations of the line. Okay. But it's a point tester. It's just like the equation of a line in R2. It's just you need more of them if you're in R3. Everybody on board? Okay. Point of policy. In this course, if a question gives you a parameterization and the question says, find the symmetric equations for the line parameterized by, as given. You have to show me the process. Now, good news, the process is really easy. Solve for t. That's it, right? But you do have to show me that process. You can't just say, again, this is a matter of policy. This is a subheading under, I'm not interested in answers, I'm interested in ideas, right? I'm interested in reasoning. Give me the reasoning. Don't just give me the answer. I don't need the answer. I know the answer. I need your reasoning. I need to make sure you understand that reasoning. Right? 2 seconds. So, again, now you might notice, and students love to notice stuff like this. Oh yeah, okay, so what you do is these numbers just go there, there, and these numbers, color change. These numbers just go there, and that's how you do it. That's not an argument, right? I want to see the process between there and there. Yeah, you had a question.
Can you repeat the wording of the sample question you just gave?
Oh, yeah, so the sample question would be like, suppose I give you a parameterization like this, and I say find the symmetric equations for the line parametrized as follows. Something like that. Yeah. Okay. Again, so the point to this policy is, the broader point is the big idea here, and that is that I'm interested in mathematical reasoning. I'm not interested in right answers at the bottom of the page. Okay. So so here's the thing. We've got 3 equations here that are the symmetric equations, and I could ask individually, what do those individual equations mean? That's a reasonable question, right? I got 3 equations here. What about just this one by itself? What's that thing? Is it I know altogether this is a line. This is the symmetric equations of a line, but by itself, what is that? And it turns out there's a wonderfully convenient answer to this question. And the reasoning is good use of ideas that we've already talked through, and one more. So the first observation I'll make about it: this is the equation of a plane. Just an algebraic appeal. Now, it's not written as ax plus by plus cz equals d, but you move things around. This is something times x plus something times y plus 0 times z equals something. So that's a plane. Okay. Next observation I want to make about this, and this is a little subtle, but the line in question that we started with is a subset of this plane. Said differently, this plane that we're looking at contains our original line. Now let me persuade you why that is. To be on the line, being on the line requires that both of these equations be true. Now, here's an immediate appeal. If both of those equations are true, then certainly the first equation is true. That's a freebie, right? If 2 things are true individually, one by itself is of course true. Okay. Well, this thing here is what it means to be on the plane. And so because of the fact that 2 facts imply 1 fact, that means that any time you have a point on the line, that point on that line must also be a point on the plane, and that means the line is contained in the plane, or the plane contains the line. So algebraically, it's a simple matter of, you're allowed to throw away free information if you want. It is perfectly legal to throw away free information, right? Geometrically, the interpretation is the lines inside the plane. Is everybody on board with that? I think it's a nice little sort of reference to logic. Yep.
Could a line just be the intersection of 2 planes, or does that have to be like all 3?
I don't understand your question.
Like if you...
So two planes can intersect to make a line, and they usually do. That's true. I don't understand.
All 3 to describe.
You don't have to. I'm just, you're getting a little ahead of me here. But what we're going to, let me come back to you in a second. Right. Okay. Okay, so we know we're looking at a plane. We know we're looking at a plane that contains the line. And there's a third thing that we know about this equation here. This equation, there's no z's in it. That means you can change z however you like. Knock yourself out, whatever. If you've got a point that's on this plane, and then you change the z coordinate, okay, so what? The equation still works, right? That means that you can change z however you want, and it doesn't affect whether the point is or is not on the plane. And I claim that means that the plane has to be parallel to the z-axis, right? If you've got a plane that has the feature that any point on that plane, you can change the z-coordinate however you want, and you remain on that plane, right? That means that your plane is, you might say, made up of a bunch of vertical lines, and therefore this plane is parallel to the z-axis. Okay, so all 3 of these together a plane containing the line that's parallel to the z-axis. The picture I like to draw for that is like this. This is the plane in reference to the line that we're talking about here. And I like to call this the vertical shadow. Right? This is the vertical shadow in the sense that if the sun were straight up, right, that sun would make a shadow out of this line, and that shadow would sort of make the shape of a plane. That's what this plane is. Is everybody on board? Okay, so to your question, what I've shown is a geometric interpretation of one of these equations. Right, we've looked at this. We see this is a shadow plane parallel to the z-axis. I'm going to leave it as an exercise for the class to do on your own. This is a shadow plane parallel to the x-axis. Now think it through. Right, there's details to be checked, like with the checkerboard problem at the beginning of the class, right? Make sure you got to make sure the reasoning actually works through, and how does it have to be adapted? It's a little bit different. Does something go terribly wrong? You got to check it. Right? And then likewise, furthermore, this is the equation of the shadow plane parallel to the y-axis. So there's three different arguments to be checked there. Now how do you want to interpret this? You could say that means that this line is the intersection of all three of these planes. Now, point of order, yeah, you're quite right. I mean, it is also the intersection of any two of these planes. That's right. It's also fine, right? But it's kind of a more interesting statement to say not only is it the intersection of two of these planes, it's the intersection of all three of them. That's sort of more geometrically meaningful. So I'm not sure. Did I answer your question? Does that make sense? Okay, cool. Right. Alrighty. Okay. Again, I encourage you to do those exercises, right? Take the time, think it through, make sure you can persuade yourself what this plane is and what that plane is. Yep.
Is it possible that all three planes do not have one line of intersection?
Nope. Because, again, you go through the reasoning, right? So, all three of the steps are going to apply, and so these planes. So this is not three random planes, right? This is three very specific planes, and so it's always going to do this. Yep. Right. Okay. So we've already kind of talked about the puzzle aspect of this material in this section. I'm going to give you some geometric things and ask you to find related geometric things. And how do you solve those puzzles? So here's the big strategy for solving the puzzles. You got to think through two things. First of all, what do you have? What do you need? What do you want? Right? And don't think algebraically. Think geometrically. Identify geometrically. Right? What do you have? What do you want? And then think geometrically about how do my tools allow me to get from what I have to what I want, right? So we already thought that through for this puzzle back here, this one, right? I have points in the plane. I want a vector perpendicular to the plane. How am I going to turn this into this? And we thought about our various tools, vector subtraction, right, cross product. Those, you put those tools together in a certain way, it solves the puzzle. Okay. All right. So the reason we have you go through and solve various of these kinds of puzzles is because playing around with things is a great way to get functional familiarity with how they work and what you can do with them. You learn what you can do with things by doing things with them. So that's what's going on here. So, for example, suppose I give you two lines through a point. Now, specifically, these are two lines through the same point, a single point. Right? And suppose I want you to find the plane that contains both of those lines. Right now, geometric appeal, if you have two lines going through the same point, there's going to be a unique, as long as the lines aren't the same line, obviously, right? There's going to be a unique plane that goes through both of them. How do we find that plane? Yep.
Well, could you use the cross product?
Oh, yeah, we are. Yeah, right, yeah. I'm sorry, my question was rhetorical.
Oh.
Yeah. but you're exactly right. You're exactly right. So here, but let's take this one step at a time. Going with the suggestion I'm making about procedures, identify what you have. I've got a point that's on this plane that I'm looking for. I've got two vectors parallel to this plane that I'm looking for. What do I need? I need a point in the plane. Okay, cool. I've already got one. Right? And I also need a normal vector. Oh, I already have it drawn over here. So there's what I want, there's what I need. Sorry, there's what I have, there's what I need. Right? And the puzzle begins. You're exactly right on what to do. We focus on the fact that we have two vectors parallel to the plane. We want a vector perpendicular to the plane, and the cross product totally does that for us. The cross product turns that into that. Okay. All right. And details, I'll let y'all think about the details. Okay, here's a weird one. Suppose I give you two planes. Now let me be a little bit more precise here. Suppose you have the equations of two planes. Right, and these things get kind of hard to draw at some point. There's two planes. These two planes, typically planes intersect to make a line. Of course, they don't have to, but in this case, the premise of the problem is that they will. I'm giving you two actual planes, and they actually will intersect in a line. This line of intersection, right, is what I want. So, and in particular, I want a parameterization. Sorry, colors. Parameterization of that line of intersection. So how do we actually get this done? Well, I have given to me a couple of normal vectors. What do I want? Well, let's see here. I am going to need a point on that line, and I'm going to need a vector parallel to that line. And so play the game again. Now, here's another geometric appeal, and again, you've got to, some of these things you have to see geometrically, right? So you cannot turn these kinds of questions into a finite list of algorithms that, here's algebraically you plug in the following way, right? You're going to have to, every geometric scenario is different. You got to think through the geometry. So my appeal is this. This vector v that we're looking for, it's parallel to the line. The line is inside the planes, both of them. Therefore, this vector v is parallel to both planes. If it's parallel to both planes, then it's perpendicular to both normal vectors. So, in fact, again, we're in this familiar scenario where I need to figure out how to turn two vectors into a vector perpendicular to both. And the cross product does that. Now, there's an unavoidable geometric, you've got to think it through and see it correctly geometrically. Right? So, you've got to develop that geometric intuition for this kind of thing. Okay. There is no sort of purely algebraic version of how to think through problems like this. Okay. All right. Last example I'm going to show you. How are we doing on time? Yeah, we're good. Okay. So, suppose I'm given two lines, again with parameterizations. So I'm given points and direction vectors. Right? I want an equation for the plane that's parallel to both of them. Now, wait a minute. There's lots of planes parallel to both of them. Right? I mean, if I have a line there and a line like that, there's two different directions. Those directions define a normal vector, but you could sort of move such a parallel plane kind of through in a bunch of different ways, right? So specifically, I don't want just any old random plane. I want the plane that's parallel to both and halfway in between, equidistant, right? Now, I think it's a pretty easy appeal to argue that well, these two vectors, if you take the cross product of those two vectors will give you the normal vector perpendicular to the plane that we want, right? So again, it's a matter of looking at the picture and thinking through about, parallel to this, perpendicular to that. Make sure the geometry actually is true, right? So no problem there. The twist on this one is, how do you find the x naught? It's tricky. And I claim what works is the x naught that you want to use is just the midpoint halfway in between the two given x1 and x2. Now, it's not obvious that that's going to work, right? So all that says is that these distances are equal. That's not what I want to know. What I want to know is that these distances are equal. I want to know those two purple distances are equal. They're not the same as the two red distances. Right? So let me give you the argument. I didn't write it down in the notes. I think this is nice to write down sort of actively. So let's see here. So let me do this with a pencil. I'm going to observe that, let's see, I'll do this with purple. Okay, so I can talk about this vector. I'm going to make this choice, right? We're going to define x naught to be that. Now I just need to prove to you that we have the equal distance that we're hoping for. I can write down that vector. That vector is x1 minus x naught. Right? And the distance that I'm looking for, I appeal to your sense of geometry. That distance, well, it's the component in the direction perpendicular to the plane. Said differently, it's the component in the in direction. So that first distance that we need to compute, there it is. There's a formula. It's the in component of x1 minus x naught. Okay, next, let's talk about this vector. That vector is x naught minus x2. Right? The distance that I'm looking for over here, that distance, well, that's the component of that red vector perpendicular to the plane. In other words, it's the in component of this red vector. So I've got formulas now. Oh, I didn't mean to erase that. I've got formulas now for the two different distances that I need to compute. I need to show that dark blue is equal to light blue. How do I know that dark blue is equal to light blue? Well, they're both in components. And it's an easy exercise to confirm, in fact, that individually these two vectors are equal. And I know that those two vectors are equal because that's a midpoint. So this is really a section 12.1 exercise. And I encourage everybody to, write down the details for that to, fill that in. But knowing that we've made this choice for x naught, you can just plain old compute both of those vectors I have circled in yellow. They are the same vectors, therefore their in components are the same, and therefore, as desired, this distance, let's see here, this distance is equal to that distance, and therefore these are equidistant. Everybody on board? Tricky little argument there. It's a nice application of components, though. That's cool. Yeah.
Did you still use the midpoint formula?
Yeah. I mean, that's what we just showed. Yeah. The whole purpose of this exercise is to show that it is, in fact, okay that this choice here of x naught being the midpoint gives us the equidistance that we want. Yeah. Okay. So there's a bazillion other kinds of examples that kind of fall into this general category of geometry puzzles with lines and planes. And so, that's going to be on the homework exercises. You'll see a million old examples on my old midterm exams, and give them some time to think about them. Yep.
What about if it were points? Because you couldn't do the same.
If what now?
If the x1 and x2 were not vectors anymore, they were points.
Well, yeah. So keep in mind, this is one of the big ideas from section 12.1 is that there is a perfect pairing between points and vectors. So these are points, right? And now, if you say, well, yeah, but I want to think of it as a vector. Okay, you can. These points have position vectors, right? But I'm using these points to describe locations, right? I'm saying that these x1 is defined as a point that this line goes through. It's helping me to define the line by virtue of its location, and that ties me down to, okay, then I must be interpreting this as a point.
But how would you figure out what that line is in terms of figuring?
But that's a given. So the premise of this problem is that you're given the two lines.
I know. I'm saying my question was if you were given 2 points, find the plane of equidistance.
That's a totally different question.
You're right. You couldn't find.
It's a totally different question. It's going to have a different answer.
But you couldn't find a normal vector.
Yeah, you can. It's a different question. Yeah, I mean, if you want to ask me about that in office hours, that's fine. But it's unrelated to this question. Yeah, and so being as it is a different question, there's going to be different inputs. I mean, different givens, different goals, and therefore it's a different puzzle, and the puzzle solution is going to be different, sort of clever reasoning. But yeah, it's totally solvable. Yeah. Okay. All right. Okay, parameterizations, round 2. So we've talked about the parameterization of a line, and you may recall, in fact, let me just flip back to this. When we talked about the parameterization of a line, I described it as, I need to generate points on our curve. Right? Well, there's nothing about lines that's unique to being able to generate points on them. Right? I could want to generate points on a circle or any other curve. Right? So the idea generalizes pretty naturally. And in general, if you've got a function that gives you position in terms of a single input variable that we often think of as time, but some input parameter, that's called a parameterization. Okay, so for example, this is a parameterization. It gives you, you'll notice, position x and y, the pair of which gives you a location, right? That gives you position as functions of a single parameter time. In this case, position is a function of time. Right? Now, in this case, this doesn't generate a line. In fact, we have to kind of think about it to figure out what this actually generates. What is this point factory spitting out, after all? Right? And a clever observation. Now, I claim that it's this circle. Here's the equation of a circle. How do I know that this parameterization is of a circle? Let me say that a little bit differently. How do I know that the points that are spat out here, how do I know that they satisfy this equation? Right? What I am doing is I'm taking points that I've generated and I'm testing them. I'm putting generated points into a point tester. I'm putting my parameterization into my equation. Right? So that's why we put a parameterization into an equation, if you want to test and see what kind of points are coming out. And notice that works, it just gives you the Pythagorean identity. So what that tells you is that every point generated here is on this circle, the unit circle. And you can persuade yourself, it's just a matter of kind of thinking it through, that as t increases, it generates the entire circle, the entire unit circle. Okay. A little bit of notation before I show you more examples. X is a function of t, y is a function of t. You can write them separately, I suppose, but you can also write them kind of together. You can say position x and y are a function of as indicated here, t. Right. Vector position is a function of t. And then since xy represents position, I like to represent position x comma y with x vector. By the way, different books make different choices here. A lot of books like to use r here. And this always kind of, look, it's very standard to use r for position. R is x comma y. And the only thing that just kind of bugs me about that is it makes me want to think in terms of polar coordinates, which we're not doing. Right, so I like to use x vector. There should never be any confusion. If I put the little vector hat over it, right, this is not a coordinate. That's a coordinate. X with no vector hat over it. Okay. Notational choices. Okay, here's another example. There's a parameterization of something. It's giving me position as a function of time. That's a parameterization of something. Right? So what is it? Let's see if we can identify what this is. And there's different ways that you can play this game. One thing that you can do is try to, I'm going to say fiddle with the algebra until out comes an equation that you know works. And one way to do that is to force it. As follows. I'm going to start with the observation that, of course, now this is position. This gives me, x and y as functions of t. So I'm going to start with the observation that x is 2 plus t. And I'm going to try to fiddle with it, mess around with it, do things to it, in the hopes of, I want to connect this to y. So y is 3t minus 5. So I'm going to try to take this thing, and I'm going to try to do stuff to it until I get y, namely 3t minus 5, to come out of it. And if I can do this, then I will have an implicit connection then between x and y. So let's get started. How do you actually do that? Again, it's not algorithmic. It's not going to be the same every time. But in this case, if x is 2 plus t, I would like y to show up. Y has 3t in it. I have a t. I want to make a 3t show up. What can I do to t to turn it into 3t? Multiply both sides of the equation by 3. Right? So multiplying both sides by 3, I get this. Now, am I done? Is this y? No, it's not, but I've made some progress. At least I have the 3t that I'm kind of looking for. Okay, well, what else do I have to do? What is it about this that's different from that? Let's see here. Well, they both have a 3t in them. Oh, I can see the difference. The difference is that I've got a 6, but I need a minus 5. What can I do to a 6 to turn it into minus 5? Let's subtract 11. Right? So with this observation in mind, that 6, fingers crossed, I would like to turn that into minus 5. We subtract 11 from both sides of the equation. Right? So subtracting 11 from both sides turns 3x into 3x minus 11. It, as desired, turns that 6 into a minus 5. I then recognize that 3t minus 5, that is the y that I was hoping for. And lo and behold, I have what I wanted. I have, again, just by kind of messing around with it, I have generated a relationship between x and y. Namely, I have an equation that all of these points on the parameterizations all satisfy. Yep.
Can you do the same thing where you can assume y equals 3t minus 5 and then manipulate the side of x?
Yep, totally. No problem. So there's no single way to do this, right? Now my instinct there is that, I tend to prefer multiplying to dividing, right? But you could totally do that. Yep. Okay. All right. So we've got a line. Now, I will point out that there is sort of a little bit of a conceit in this presentation that I just gave. I started off with what is, in fact, a perfectly respectable representation of a line. And I turned it into A different, perfectly respectable presentation of a line. All I did really in turning this into that is I made it something that's maybe a little bit more familiar, maybe a little bit more recognizable. Right? It's not like though that this is somehow better. Like this is, that is the, algebraically that's the line, and I don't know, this poser thing over here that we started with, I don't know what it thinks it is. Right? That's just not the case. They're both algebraic relationships that describe the geometry in question. But again, sometimes one or the other is more familiar. Okay. And I'm out of time, so we will pick up here on Friday. Yeah, see y'all later. Have a good day.